Size. Nepali. Sai is doing his Ph.D. in chemistry with physics as a co-discipline. Nathan Euler and I have been Sai's co-advisors. So Nathan Euler is the committee chair and we're both research advisors. We worked together on this program. And this is great. We've got a bunch of people on Zoom, a bunch of people in the room. So we'll do our best to coordinate. We can hear pretty well everybody on Zoom and they should hear anything up front. I think everybody can hear me on the computer, right?
Maybe see you too.
Okay, cool. All right. I'll let Nathan say a few words. He's in Belgium right now. So he's coming to us through the interwebs.
Yeah. So it's my pleasure to introduce Sai. And actually, he wrote a very nice vita at the end of his dissertation. So I'm pretty much going to read it. Sai was born in Anantapur, a small town in the state of Andhra Pradesh, India. He completed a BS in 2011 in chemistry and a Master of Science in chemistry, both from the Sri Sathya Sai Institute of Higher Learning in Anantapur, India. So after his MS, but before he came to do work here at UMKC, he spent a year, I think it was, as an assistant, maybe more than a year, as a research assistant in the NMR Research Center in the Indian Institute of Science in Bangalore. He came to UMKC in the fall of 2017, and he joined my research group and Michelle's research group sort of simultaneously in, I think it was spring of 2018, and has been working with us on a NSF funded grant that's he's going to tell you a lot about today. I'll mention a little bit more about that in a second, but he, as part of his studies, he did the Preparing Future Faculty Certificate Program offered by UMKC and has been a graduate teaching assistant, a graduate research assistant, and has guest lectured as part of his PFF studies for example, in my physical chemistry kinetics course or kinetics section. His expertise, and I sort of should emphasize the word expertise, spans the field of chemistry, condensed matter physics, and incorporates synthetic chemistry, physical chemistry, thin film deposition, vacuum work, materials characterization, all sorts of instrumentation. And post-graduation here, he aspires to launch his professional career in industry and has already lined up a job to do so. So the work that you're going to hear about today, this investigation of process structure property correlations for plasma-enhanced chemical vapor deposition, complex disordered solids towards data-driven computational materials design, is basically encompasses pretty much the scope of the NSF project that I mentioned before, which is a collaboration between myself, Michelle, Dr. Paul Rulis in physics, and some external collaborators, another theoretician, and another experimentalist working in Ohio and Missouri State. Sorry, the other way around, Missouri State and Ohio. And you know, I'd like to sort of say one last thing, which is that when you go through this talk today, please understand that literally every experimental data point, every synthesis, every characterization was performed by Sai. So this is his work from beginning to end in all of the experimental stuff in this talk was done by Sai. So take it away, Sai.
Thank you, Dr. Euler and Dr. Puckett, for the introduction. Good afternoon, dear professors and colleagues. Good afternoon, everyone. Thank you for attending my presentation, both in person and on Zoom. I'd like to take this opportunity to introduce my other committee members, Professor Rulis from physics, Professor Peng, and Professor Chen from chemistry. I'm not going to say the title. The title is too long, but it justifies my research work. So this is the outline of my talk. It basically follows the same format as my dissertation. Let me begin with my motivation and objectives. So I'd like to start off by talking about local structure and disorder. In the context of materials design, experimentalists take trial and error approach, which involves synthesis, characterization, and testing to achieve a presumed target. The idea here is to tune the local structure, but this local structure exists in numerous configurations ranging from crystalline to non-crystalline forms. So let's first look at the simple single component systems. Crystalline silicon exists in cubic crystal form with its perfectly ordered silicon arrangements, which have a long range order showing up to a few tens of angstroms. And one could perturb this stable system by introducing dopants without altering the crystalline structure to create charge defects that forms the basis for N or P type semiconductors. Another variant is amorphous silicon or amorphous hydrogenated silicon, which lacks long-range order that was seen with the crystalline materials due to imperfect arrangement of silicon atoms with disorders in their local structure, such as dangling bonds and SiH terminal bonds. And the effect of local structure is exemplified by the allotropes of carbon. In the case of amorphous carbon or amorphous hydrogenated carbon, the structural complexity increases due to the random arrangement of carbon atoms, along with different hybridization states that carbon exists in, and CH terminal bonds. So the complexity further increases if you were to combine these two elements. For example, even crystalline silicon carbide exists in various forms, including in cubic lattice and hexagonal lattice. And considering the amorphous silicon carbide or amorphous hydrogenated silicon carbide, it lacks a long-range order due to numerous configurations which are characteristic that are connected to each other randomly and making these materials way more disordered compared to single component systems such as amorphous silicon or amorphous carbon. This foundation leads me to define what complex disordered solids are. So these materials refer to functional materials that consisting of multiple elements which exist in either mixed phases or segregated phases. Some of the examples include amorphous hydrogenated silicon carbide, amorphous hydrogenated silicon carbonitride, or silicon carbon oxynitride. Other examples include metallic glasses and high entropy alloys. Complex disordered solids are further characterized by substructures which have a direct correlation to the precursor from which they are made from. In this dissertation, we are primarily focused on molecular precursor-derived complex disordered solids, and I'm going to talk more about molecular precursors in the later slides. So in simple terms, complex disordered solids combine the functionalities of simple materials and exhibit a wide range of properties. A common feature is that these materials lack periodicity, and the local structure exists in numerous configurations, and which poses unique challenges because there is no straightforward experimental technique to characterize the structure. On the other hand, these materials rather would require multiple characterization techniques, including NMR, nuclear magnetic resonance, X-ray photoelectron, or infrared spectroscopies, along with diffraction, to establish these local structures and how they are connected to each other in 3 dimensions. Moreover, the structure of these materials strongly depend on the properties, which makes the determination of process structure property relations laborious. And after all, this disorder is not necessarily a disadvantage. We could exploit this complexity and their process dependence to control the structure and modulate the properties. So plasma enhanced chemical vapor deposition, PECVD, is one of the widely used semiconductor processing techniques that offer variables to tune the structure and properties. PECVD is a complex process, and a cartoon representation is given on your left. A plasma is generated between 2 electrodes, and in this work, we used inert argon plasma. So chemical precursors are introduced into plasma where they dissociate into reactive species and then recombine to form polymers and settle down on the substrate. For a reactor configuration, there are usually 4 major process variables: plasma power, which affects the energy available for gas-phase reactions in plasma; temperature affects the thermodynamic reactions happening on the substrate surface; Pressure indirectly affects the plasma energy and plasma density. Precursor flow defines the reactant flux of the precursors in plasma, thereby controlling the kinetics of this deposition. So in this work, we studied thin film complex disordered solids in the form of thin films. The question is, how do we choose an optimum condition based on these parameters for a targeted structure or property? It is a non-trivial task which requires a comprehensive understanding of the influence of PECVD parameters on structure and properties. It would have been easier if we had the ability to simulate these fabrication processes, but unfortunately, we cannot reliably do so with the existing computational methods. So conventional molecular dynamic simulations uses melt and quench strategy, which involves packing a simulation box with molecules, increasing its temperature, and then cooling it down to an amorphous state. Unfortunately, these simulations do not consider the non-equilibrium process that are actually happening in fabrication processes. And these simulations cannot retain the substructures associated with multiple potential minima on a vast potential energy surface diagram. So if you look at this free energy versus structural configurations graph, there is a global potential minimum that exists associated with a more ordered or crystalline form, but there exist several structural configurations that belongs to metastable potential minima. And these molecular dynamic simulations cannot capture all of these configurations. The other drawbacks include their small volume simulation, obviously, which cannot capture all the configurations, and their inability to replicate real-time process timescales. And the imperfect intratomic potentials that guide the structure evolution during these simulations is also not well developed. On the other hand, reverse Monte Carlo simulations involve random adjustment of bonds and angles to match the computed data to some experimental data, such as diffraction. The output models generated in this simulation may not be physically relevant, as it is a purely math-based simulations. So, but however, there exists enough efficient theories to calculate properties if a precise structure is given. The fundamental problem revolves around establishing this structure. And even if a structure is established, how do we relate process parameters to structure? Hence, the chemistry-informed machine learning approach is sought to map the underlying process structure property relations rather than reproducing the fundamental physics or chemistry. So when I started this research work in 2018, the idea of data-driven computational design seemed brand new. But since then, significant improvements have been made on all fronts of computational design and discovery, including building cyber infrastructure, developing novel algorithms, and high-throughput calculations. This project was funded by NSF division, as Dr. Euler mentioned, and it was shared between 5 PIs across 3 different institutions. The overall project scope is divided into 3 sections. The first one, denoted in red, belongs to experimentation, which involves the selection of suitable molecular precursors and the fabrication of structurally different complex disordered solids. While doing so, characterize the plasma processes, elucidate the structure and properties of thin films by several techniques, and assemble the process structure property dataset together. And the second section, denoted in blue, briefs the computational efforts where the experimental data generated can be used as constraints to guide molecular dynamic simulations and their subsequent structure refinements by hybrid reverse Monte Carlo simulations. I'm not going to go more into details, but this part is handled by Professor Rulis from UMKC and Professor Sakija from Missouri State University. And the experimental part is handled by Professor Euler, Professor Puckett, and Professor Hong from Ohio State University. So once the simulation protocol is optimized, the idea was to generate a large set of structural models and train with a suitable machine learning algorithm to enable data-driven materials design and discovery. As an experimentalist, my role was associated with materials fabrication and characterization, and hence the objectives of my dissertation were twofold. One, to fundamentally understand the process structure property correlations for complex disordered solids, and to curate an experimental database to guide the atomistic simulations. So the first question that we had to address was what materials to study. Amorphous hydrogenated silicon carbonitride was selected as a representative class of complex disordered solids based on the compatibility of the composition with several structure characterization techniques and the ease of precursor synthesis for those and stability of those compounds and the available research budget. Of all the elements considered which are capable of forming disordered solids or ceramic materials, silicon, carbon, and nitrogen are compatible with most of the structure characterization techniques, including XPS, NMR, FTIR, electron microscopy, and neutron diffraction, although we might need 15N isotopic labeling for NMR studies. So boron is not an ideal element for neutron diffraction studies because 10 boron isotope absorbs neutrons and undergoes further nuclear reactions. Oxygen is a non-magnetic nuclei and is not compatible with NMR. Fluorinated precursors are expensive to be considered for a detailed study like this, and aluminum and phosphorus containing precursors were also expensive and highly reactive, which requires inert handling conditions. Fortunately, our choice of materials, silicon carbonitride, has numerous applications in electronic and optoelectronic industries. For example, they are used as dielectric layers in integrated circuits and electrode materials in lithium-ion batteries. So the next question was, after choosing the materials, the selection of molecular precursors was important. As I mentioned earlier, our focus was to use molecular precursors to study complex disordered solids. Molecules are the simplest chemical species that can impart substructure and offering diversity to the complex disordered solids. At the beginning of our study, we chose these 4 different precursors based on distinct bonding configurations and their relative atomic compositions. The PECVD process requires that these molecular precursors have sufficient vapor pressure to transport these precursors into the deposition chamber. And also their reactivity to form thin films, availability of synthetic routes for special circumstances like isotopic labeling for NMR, and the commercial availability of precursors under our reagents and their cost effectiveness. Hexamethyldisilazane has a distinct silazane chemical moiety, which was commercially available. Diisopropyl vinyl methylsilane diamine, abbreviated as DIMVS, was and its cyclic derivative, abbreviated as DIDMDVDS, were synthesized in lab, and these are novel precursors which haven't been reported before. These are designed to have a vinyl group to increase its propensity towards its polymerization, and the ring strain to increase its reactivity. Bis trimethylsilyl carbonamide BTSE was also synthesized in lab with the carbon double bond nitrogen moieties to impart structural diversity to the materials. And these precursors, the synthesis and purification procedures for all these precursors have been optimized, and the compounds are characterized by NMR. And these schemes can be used to label the precursors with the 15N isotopes. So out of these 4 precursors, hexamethyldisilazane-derived amorphous hydrogenated silicon carbonitride films was extensively studied to understand their process structure property relations. And chapter 3 of my dissertation describes these correlations in detail. But here I'm going to highlight a few key results. We employed full factorial design of experiments in which each PECVD parameter, as I mentioned earlier, temperature, pressure, power, and flow rate, was considered at 2 levels, high and low, which represents sort of a reasonable extremes compared to the literature values. The advantage of factorial design is that it considers all the 16 possible combinations, because if you have 4 variables, it leads to 2 power 4, 16 different combinations of these parameters. And it also reduces the number of experiments to be carried out to understand comprehensively the relations between the parameters and their properties. And also, it also tells us the effects of individual parameters and parameter interactions on effects on the properties. And while doing this, we acquired several properties of the thin films, like thickness and refractive index from spectroscopic ellipsometry, optical band gap from UV visible spectroscopy, composition from XPS, and chemical bonding information from FTIR. The objectives of this work was, again, to understand the influence of PECVD parameters on a-SiCN H films, fabricate structurally distinct materials for our overall project scope, and curate a process structure property datasets. I'd like to highlight the data acquisition and analysis strategy involved with the factorial design. So in our design, we had 16 different experimental conditions, each representing unique PECVD conditions. So for each condition, we deposited multiple and randomized deposition batches of thin films to understand the variation in fabrication processes. And within each deposition, we fabricated multiple thin film samples. You can imagine keeping multiple substrates in the center of the bottom electrode in PECVD. So an average response or property was calculated from all the samples where applicable, such as in the case of spectroscopic ellipsometry. And the average response from multiple deposition batches was combined to calculate a combined average response, which was then used in our statistical analysis by ANOVA. Now, this is the data set of the factorial design looks like, and we perform statistical analysis on this data set. So spectroscopic ellipsometry involves uses the plane polarized light that incidents on the thin film surface and reflects back to the detector. The reflected light is elliptically polarized due to the changes in phase and amplitude. And the changes in phase and amplitude represented here as psi and delta are plotted against the wavelength, and a Cauchy model representing a transparent thin film on silicon substrate was fitted to this experimental data to extract thickness and refractive indices of the films. The growth rate was then calculated by dividing the thickness and the deposition time for the film. And the effects of PECVD parameters, temperature, power, flow rate, and precursor, and their two-way interactions on the growth rate was studied using a Pareto chart. This is basically a bar chart which tells us the effects of individual parameters and their interactions. And the negative and positive effects are clearly evident from this graph. And moreover, in addition, the statistically significant effects are color-coded in red. So the temperature and plasma power was found to be most significant parameters, and we deposited a series of thin films at different substrate temperatures to understand its effect in detail. A similar Pareto chart was developed for refractive index. Again, temperature was found to be most significant in affecting these properties. A linear prediction model was developed based on the main effects and the interaction effects to estimate the refractive indices. For example, if you look at here, these are the red spheres indicate the predicted values from the model, and the stars represent the experimentally determined model. So these models were validated by experiments conducted in the central points of the factorial design, and model seems to be accurate within 2 to 9% relative error, which was surprising. Optical band gap for these films was determined from ultraviolet visible spectroscopy. The absorption coefficient data was plotted against the photon energy using a tau relation for the disordered materials. According to tau relation, the x-intercept of this slope gives us the band gap for these films. Again, a Pareto chart was made to understand their effects. Band gap seems to decrease with increase in temperature, and a linear model was also developed to predict band gap values, which was accurate under 10% relative error. We used XPS to estimate the elemental composition. XPS relies on measuring the binding energies of the core electrons of atoms. The binding energies of the electrons are specific to atoms, which makes XPS a robust technique to quantitatively estimate the elemental composition. And this is an example XPS wide scan spectrum of one of the samples. XPS was acquired on as deposited thin films after sputtering the surface with argon to remove adventitious carbon, so that we are probing the bulk of the thin film. We were able to tune the composition of the materials with respect to HMDS composition as a function of PECVD parameters. The variation was good, but the variation was not as we anticipated. It wasn't drastic. And the Pareto chart for example, the SiC atomic ratio was analyzed, and the SiC atomic ratio tends to increase with increase in temperature. And our XPS data was also corroborated by the composition determined from a specialized technique called nuclear reaction analysis and Rutherford backscattering spectroscopy. Again, as similar with other responses, the linear model was accurate, relatively accurate under 10% relative error. So in chapter 3 of the dissertation, basically we studied the influence of PECVD parameters and elaborately understood the process structure property correlations. We were using factorial design. We were able to tune the properties and compositions as a function of PECVD parameters, and the use of factorial design to study a-SiCN precursors such as HMDS was new. It was not reported in the literature. And as part of this, we fabricated structurally distinct samples and curated these process structure property datasets. Linear prediction models for process property relations worked really well, but it failed to predict properties for the conditions that fall outside the factorial design conditions, which suggests that the process property relations are not linear, moreover, these linear models were rudimentary, by which I mean we did not consider the structural aspect of the thin films. We directly tried to predict the properties from process parameters, but it offered a quick and dirty way to optimize the material and properties. A robust predictive design would require the consideration of structure and link the structure to properties. So in chapter 4, we channeled our efforts in structure characterization of these materials. So the structure characterization for disordered materials can be done at different length scales, including short range order, medium range order, and long range order. Short range order is confined to the local structure, probably to a single bond distance of 1 to 2 angstroms. The possible local structures for the proposed materials include SiN4 or SiC4, or it could be a mixed environments where silicon is bonded to both carbon and nitrogen. And a variety of hydrogenated bonds or homonuclear bonds could also be present in these materials. And structure at this scale can be elucidated by NMR, XPS, FTIR, and diffraction. And on the medium range order scale, which is approximately 2 to 6 angstroms corresponding to 2 or 3 coordination spheres around the local structure, can be elucidated by NMR and diffraction. And long range order, which is greater than 6 angstroms correlations, can be elucidated by diffraction studies. As we increase the length scales, the structural complexity increases, and it is really difficult to characterize the structure experimentally. In the next few slides, I'm going to show how we use these different techniques to establish the disordered structure. So FTIR infrared spectra were acquired on the as-deposited thin films, and the characteristic vibrational signatures have been assigned to chemical bonding configurations based on experimental and theoretical literature. Notable stretch assignments include NH stretch, several methyl and methylene stretches, which indicate the presence of terminal methyl groups and methylene bridges in the material. SiH stretch was unique, which was not present in HMDS precursor, and SiCH3 VAC. At elevated temperatures during our deposition, the CH stretch region and the fingerprint region of the spectrum became diffuse and featureless, indicating that the films have undergone a significant cross-linking or ceramization. A detailed analysis of the variation of the structures is presented in the dissertation. Apart from the elemental composition, we also used XPS to probe to understand the qualitative chemical bonding structure. Binding energy shifts for specific atoms are associated with their bonding environments. For example, N1s spectrum of XPS was fitted with 2 peaks. One peak was corresponding to nitrogen bonded to silicon. The other narrow peak was corresponding to NC bonds. The evidence for the presence of NC bonds comes only from XPS because XPS is very sensitive, and this peak corresponds to only 1 to 2% of nitrogen in the overall thin films. And the similar way, carbon 1s spectrum was also fitted with 2 peaks, one peak corresponding to carbon bonded to silicon, the other peak corresponding to both CC or CN bonds. And silicon 2p spectrum was fitted with 1 peak ascribed to silicon in the presence of a mixed environment. So the chemical assignments to the peaks were done based on the binding energy values after calibrating the spectra to argon 2p3 halves peak at 241.9 electron volts. So one of the challenging part in the structural characterization of these materials is the sample requirements for experimental techniques. In the factorial design experiment, we fabricated thin films up to a thickness of 200 nanometers on a 1.5 by 1.5 centimeter silicon wafers. The sample collected on these surfaces was approximately a few micrograms. But for NMR and neutron diffraction, they required 30 milligrams or 150 milligrams of the sample, which was a huge challenge. So for the synthesis of bulk materials, we developed 3 different approaches. The first one included the deposition of thin film on a large surface area silicon wafer and scrape the film off the silicon after deposition. This approach really worked well for samples deposited at low temperatures, but for at elevated temperatures, the films were very adhesive and hard. We couldn't scrape the film off the silicon wafers. In the second approach, we deposited films on aluminum foil and later dissolved the foil in dilute hydrochloric acid. And this worked really great for all the samples, but we realized that it significantly altered the composition of the films by incorporating oxygen, which was not good. The advanced structural characterizations that we did in this work were based on the samples that obtained from the aluminum foil. So I was struggling a bit to find out ways to make these pristine materials. So we deposited films on different metallic substrates such as copper, zinc, and aluminum with contrasting thermal expansion coefficients compared to silicon carbide. So after depositing these films, we vacuum sealed these and then cooled in liquid nitrogen. Because of this thermal expansion differences, the films peeled off at the substrate and we could collect the powder samples. Out of these substrates, copper substrate was found to be peeled off the films very nicely, and the XPS on these powder samples indicate mild contamination with oxygen. Solid state magic angle nuclear magnetic resonance was performed on a select few a-SiCN etched powders that were deposited at different temperatures. For the sample collected from the silicon wafer, it exhibited 2 resonances, one corresponding to the silicon in the hexamethyldisilazane environment, the other other resonance that could correspond to silicon bonded to 4 carbons or hydrogenated silicon. And these peaks are very broad. And the samples collected from the aluminum foil were significantly contaminated with oxygen, as noticed from their peak resonance assignments made from the chemical literature. Interestingly, the silicon resonances fabricated have broadened for the samples fabricated at higher temperatures, which indicates the onset of a high degree of cross-linking at about 240 degrees Celsius. Advanced structural characterization experiments, including correlation experiments, needs to be done for these samples. The synthesis of pristine materials was an impediment to do more nuanced studies. And we performed neutron diffraction experiments on 3 powder samples at Oak Ridge National Laboratory. We secured beam time through a proposal, and the experiments and analysis was performed by the instruments scientist, Dr. Newfriend. Paired distribution functions, or PDFs, represent the paired correlations in 3 dimensions. For example, if you select an atom at an origin, and if you try to map the 3-dimensional space, as we hit the first coordination sphere, we get a peak in PDF, which is also called as paired correlation or a nearest neighbor peak. And the second or the next nearest neighbor peak corresponds to the atoms in second coordination sphere. So like this, we can establish the medium range structure and how the various local structural configurations are connected to each other. So for our samples, the peaks in the 1 to 2 angstrom range correspond to local structure, maybe to single bond distances. For example, peaks at 1.72 and 1.88 are ascribed to SiN or SiC bonds. For peaks greater than 2 angstroms corresponds to medium range structure, which requires modeling methods for better understanding. So based on these structural moieties that were identified and gathered by various spectroscopic evidences, we put them together to synthesize a couple of abstract models. Model 1 sort of represents a disordered material that is porous with the more terminal methyl groups in this model. And model 2 represents a film with a higher degree of cross-linking with fewer terminal methyl groups. We hope that the experimentally found structural moieties would guide the atomistic simulations to generate a better physically relevant models. So one another challenge that I took upon myself is to make this experimental data accessible to public through an open source database. Several databases exist globally, but none of them were open to public to contribute data. Fortunately, in 2022, that is last year, the Materials Project database created this MP contribs platform where experimentalists can contribute data. So as part of this work, we contributed the process structure property data as well as the spectroscopic data generated in our work to the database. Here is an example representation of how data is displayed on the database, including the spectroscopic information. And these data can be programmatically retrieved and compared with our simulations, or can be downloaded as a Excel or JSON file. I should say we are one of the early adopters of contributing data to open source databases, especially for PECVD derived thin films. So after completely analyzing the hexamethyldisilazane-derived silicon carbonitride thin films, we went on to perform the similar analysis for the other two precursors using factorial design. So we were able to tune the properties of these two precursors as well, similar to HMDS, and the composition were also weighted. The hollow triangles and hollow hexagons represent films derived from BTSC and DIVMS precursors. The compositions were different when compared to HMDS molecule, but as I said, the variation was not as much as we expected, but still we see a good variation in these films. A preliminary analysis of the FDIR reveals that the BTSC derived films contains carbon double bond nitrogen moieties along with the terminal methyls and methylene bridged carbons compared to HMDS. One thing that we observed was it incorporated a greater percentage of nitrogen in the films compared to HMDS, probably due to nitrogen existing in strong carbon double bonds in the precursor. DIVMS precursor derived films exhibited simple structural moieties such as terminal methyl CN and CC bonds. And interestingly, it incorporated lesser amount of nitrogen in the films compared to HMDS films, even though the precursor had two nitrogens in it. So overall, molecular precursors dictate the composition and substructure of these fabricated thin films, supporting our initial strategy of choosing different structurally different molecular precursors. As part of a future work, I laid out a few short-term goals and long-term goals. Advanced NMR studies on HMDS-derived films needs to be carried out to understand the local structural connectivities by correlation experiments, and we have to complete the DOE for BTSC and DIMBS precursors is not complete yet, so we have to finish that and then contribute the data to MP contribs. For long-term goals, plasma processes need to be rigorously characterized by optical emission spectroscopy to understand what's happening in the plasma. And we could replace argon plasma that we used in this work with nitrogen plasma to alter the composition of the films further, or expand the process range by combining the annealing studies after depositing the films. Quantitative structure characterization is an important aspect, which would help to define the models very accurately. And there also exists a variety of precursors that needs to be studied to understand the effect of molecular structure on complex disordered solids. To kind of close the loop with my objectives of the dissertation, we successfully fabricated molecular precursor-derived amorphous hydrogenated silicon carbonitride as a class of complex disordered solids. And while doing so, we understood the process structure property property correlations and develop the process structure property database. Some of the notable contributions from this work include the synthesis of novel precursors and adopting factorial design of experiments to study a-SiCN molecular precursors and understand their process structure property relations, and contributing the experimental data on PECVD derived materials on MP contracts. I hope I've done my work, and I'm eager to see how these data are utilized in simulations and receive feedback from them. This work wouldn't have been possible without the help from a lot of people. I'd like to express my sincere gratitude to my advisors, Professor Euler and Professor Puckett. Thank you for this wonderful opportunity, for your support and encouragement. All my academic achievements and progress in this research wouldn't have been possible without your guidance. And I'd like to thank my committee members, Professor Rulis, Professor Peng, and Professor Chen, for agreeing to serve on my committee and providing timely feedback on my research endeavors. And my collaborators, Professor Sakija, Professor Hong from Ohio State University, Dr. Niffin from Oak Ridge National Laboratory, and Chris Benmore from Oregon National Laboratory. They helped me with understanding the complicated diffraction experiments with neutrons and synchrotron X-rays. And when I first joined this lab, I received tremendous help from the doyens of the group, Dhanendra, Shailesh, and Rupak. I harassed them more with questions in condensed matter physics, and thank you for being patient with me. And my colleagues, Raja, Andrew, and Michael, thanks for your teamwork and friendship. And I also worked with lots of undergrads, high school students, and collaborators from the computational groups. So thank you all for working with me. And I would like to thank all the professors from chemistry and MIT for their support and encouragement. Professor Kilway, thanks for the opportunity to study at UMKC, and Professor Caruso, who encouraged us at all time, and he has our back. Last not but the least, I'd like to extend my thanks to my family and relatives for their support on lab, and the wonderful audience for your patient listening. Thank you.
Awesome. All right. So we will start with questions from the audience, both in the room and on Zoom. And then once everybody's answered everything that they wanted to know, we can move to just the Q&A. So questions, where do we want to start? Okay.
Yes.
Going. We'll start with a non-technical question.
Okay.
Why proactively put your data on an open access platform?
Because we would like people, computational physicists, or to use this data and then develop suitable models. We want the data to be more accessible. So there is other significant developments happening where people are trying to mine the literature from the journal papers, which is more difficult because the data is in a graphical form or tabular form, so it's pretty difficult. So we want to put in a database which can programmatically retrieve. Yes.
One of the biggest things about machine learning is some people kind of view it as a bit of a black box. So what do you think is the biggest challenge for taking this data and making more of a traditional theoretical model with it?
Okay, the question, I'm going to repeat the question for the audience on Zoom. So the question was, machine learning is understood as a big black box. So what can be done to make it more understandable? I'm not an expert on that, but whatever I had read from the literature, there is this new concept of explainable artificial intelligence. So new algorithms are being made. So for example, if you think about artificial neural networks, they use the hidden layers, which are called as black boxes. It relates the inputs and outputs, but we don't know what's the exact relation. So they're trying to develop algorithms called as explainable machine learning algorithms, which would tell us a relation, information about the relation. So it's brand new. I think I've seen one paper where they are trying to use explainable artificial intelligence to revert the diffraction data into some sort of a structural models. I hope it answered your question about this.
Questions?
Questions on Zoom?
Questions on Zoom, raise your hand, shout out if you want, go ahead, shout out.
No, there you go.
Oh, Tom's here. Okay, going once, going twice. All right, can we give Sai a round of applause? So you are dismissed.
Yeah.
Thanks for coming, everybody.
So I think we can take a few minutes for a break to allow people to leave the room.